In this session, we will discuss about internal forces in beams or frame members. So typically, they are shear force and the bending moment which happen when you cut a beam or a frame member. There can also be an axial force in a beam column type of member. So before we start discussion on how to calculate those, first thing is to lay down a certain sign convention, which so based on this sign convention, we will define whether we call a particular type of force positive or negative. So for the axial forces, if the axial forces are tensile in nature, we call them positive. And if the axial forces are compressive in nature, we will call them negative. Okay, so this is just a convention, and it will be perfectly okay to use an opposite convention, but just to be consistent in the rest of the sessions, we will choose these sort of sign conventions. Next, for moment or for bending moment, so a moment which is a sagging moment is called a positive moment, which means if the beam, let's say, was initially straight, so if it bends in this shape, or it sags towards the ground, that is a sagging moment, and that we consider as positive. And in general, this may be considered in terms of, so if this is the member, and we may define a local coordinate system. Let's say member is along x axis. Okay, so downwards of the x-axis is the sagging sort of action. For vertical members, this sort of definition may become more useful. For horizontal members like typical beams, sagging has the right notion of being sagging towards ground. So a sagging moment will be considered as positive, and the moment which causes upwards bending or hogging moment, right, so this is the hogging and this is the sagging. So the hogging moment will be considered as a negative moment. Now for shear force, the sense of shear force which increases, so let's say this angle was 90 degrees earlier, now this is more than 90 degrees. So the shear force which increases this angle, that will be considered as positive, and shear force which decreases this angle, so this angle will be less than 90 degrees. So a shear force that decreases the shear deformation angle, that will be considered as a negative shear force. Now to sum up, so this particular image or figure shows all the positive signs. So if we are cutting on the right of a member, a downward shear, a counterclockwise moment, and an outwards axial force, these are positive. Okay, and if we are cutting on the left end a member, then a leftwards axial force, a clockwise moment, and an upward shear force will be considered as positive. And similarly, if we were to plot or if we were to draw the negative sign convention, it will look like that. Okay, so so notice that in general we do not consider that all clockwise moments are positive. So if it is on the right, in an anti-clockwise is positive. If it is on the left, a clockwise is positive. And the general idea is that this has to do with sagging or hogging. Okay. Okay. Next, let's do a very quick review of the Euler-Bernoulli beam theory. We will not go into derivations because this is typically derived in a mechanics type of course. So the basic differential equation that comes out of the Euler-Bernoulli beam theory is this. This is the moment curvature relationship. So this second derivative of the displacement is the curvature. Okay, so basically we say that Euler-Bernoulli beam theory gives a linear relation between the moment and the curvature, and this is connected through EI, which is the bending rigidity. So if EI is infinity, that would mean that that particular member cannot bend, and if it is 0, that means it can bend without any additional moment. There is another form which you might have seen, which is involving the fourth derivative of the displacement, and this basically is the load intensity. So if we consider a particular span of a beam, this may have certain applied load on top. This is what Q of X is. In fact, this will be minus Q based on the sign convention. So the fourth derivative of displacement gives the load intensity, and the second derivative, which is curvature, is related to the moment. Okay, so using these we can define certain relations between force quantities and displacement quantities. So on the left here are the force quantities, which means we have bending moment, we have shear force, and we have the load intensity. And on the right side here we have the displacement quantities. We have deflection, we have slope, and we have curvature. Okay, and owing to the beam theory that we have certain relations between the forces as well as the displacements. So the shear force is basically first derivative of the moment. The load intensity is the first derivative of the shear force. Okay, and if you really consider, then the shear force is the third derivative of displacement, because M has second derivative of displacement. So so shear force is related with the third derivative of displacement, and this load intensity is related with the fourth derivative of the displacement, as we have seen earlier also. Okay, and similarly, there can be a reverse relation. So if we integrate load intensity, we get shear force, and if we integrate shear force, we get bending moment. Okay, or in other words, the area under a shear force diagram will give bending moment, and area of the load intensity will give shear force. Okay, and conversely, the slope of a bending moment diagram will be equal to the shear force value, and slope of the shear force diagram will be equal to the load intensity value. Okay, now similar things can be seen for displacements. The slope is defined as the first derivative of the displacement, so this is a well-known fact, I guess. Then the curvature is the second derivative of the displacement, or first derivative of the slope. Okay, so curvature is the rate at which the slope changes, and the reverse relations can also be found, that the slope will be area under the curvature diagram, and the displacement will be the area under the slope diagram. Okay, so these relations become very important when we start making shear force and bending moment diagrams. So they provide very easy checks to see whether our diagram is correct or not. Okay, so so the things that we were discussing are summarized in these 2 points here. The slope of the shear force diagram gives load intensity. So what it means is, if if there is no applied load intensity, right, the shear force will have zero slope, or that span will have a constant shear force. It may be zero or non-zero, but it will remain constant. If Q is non-zero but constant, which happens in a UDL, a uniformly distributed load, then we will have a linear shape for the shear force. If Q is a linear load, which means something like a triangular load, then the shear force will have a quadratic shape. Okay, and you can continue to argue this way, and you can find out the correctness or the order of the shear force diagram depending on the applied load intensity diagram. Similarly, the slope of a moment diagram gives shear force, so which means that if shear force is 0 in a particular span, the bending moment will be constant. Okay, now the bending moment may be 0 or non-zero, but it will be constant. Similarly, if shear force is not equal to 0 but constant, okay, then the bending moment diagram will be varying linearly. If the shear force is linear, the bending moment will vary quadratically or parabolically, right? And again, one can build upon this further to see that if the shear force diagram has a certain shape, what will be the shape for the bending moment diagram. Let us now look at a few examples for calculation of bending moment and shear force for a certain type of system. So in this we look at a cantilevered beam. So the span is L and there is a tip force P, and the coordinate system being shown is like this, so X and Y. So X to the right and Y upwards. Now let's say we have to find the bending moment and shear force at L by 3 from the support. So let's say at some point here, right? So first thing will be to find the support reactions. Okay, so in this case, first we draw the free body diagram which shows the support reactions. So the support reactions will be just P and PL, right? And now to calculate the shear force and the bending moment at L by 3, we cut the span at L by 3. And the shear force and bending moment we can calculate either by considering the left span or the right span, right? So let's say if we are calling this point as C, this point, right? So we can either consider AC or we can consider CB. Okay. Now if we consider AC, we will consider this as being cut on the right side. So according to the positive sign convention, the downward shear and counterclockwise moment, this will be the assumed positive sign convention. So when we consider left span, the summation of Fy equal to 0 will give S equal to P. So this S equals to P. Okay, and we can do moment balance about point C. That gives M as minus 2PL by 3. Okay, so this so like this we can compute S and M. Now this was considering left span, but we can consider the right span also. Now if we so left span when we were considering AC, and right span will be CB. So when considering the right span, we have cut it from the left. Okay, now since we have cut it from the left, according to the positive sign convention, upward shear and clockwise moment will be the positive convention. So that is what we assume here. So again, summation Fy equal to 0 gives S equal to P, and summation of MC equal to 0 gives M equal to minus 2PL by 3. So it is no surprise that the moments and the shear from both sides will come out to be same, because these are in general continuous in nature. So unless there is an applied load, the shear force will remain continuous, or if there is an applied concentrated moment, the bending moment will be continuous. Okay, so from both sides we should be able to reach the same result. Okay, let's look at another example. Let's consider a frame like this. Now again we have to find, let's say, shear force and bending moment at point D, which is the midpoint of span AB. So the point D is shown here. Okay, so again first thing will be to find the support reactions, and support reactions we find as HA equal to minus 15 and VA is equal to 8.75 kilonewtons. Although we have found VC here, if we are only interested in shear force and bending moment at D, we really need not worry about VC, because we can consider this lower span AD and we can calculate the shear force and bending moment. Okay, so for finding shear force and bending moment at D, we consider the lower span AD. Now the positive axis of Y is oriented like that. Okay, so in general, we talk about member axis. So this XY is the global axis. So we can say that for this column AB, the local axis X is oriented like this, and the local axis Y is oriented like that. Okay, so basically then we are cutting the right end of a member, right? So So this is global y but local x, x bar, and this is local y bar for the member. Okay, so the local axis is basically oriented along the centroidal axis of the member. So now basically we are cutting it from at the right end, so we may consider that downward is positive shear and counterclockwise is positive moment, and then we can write the the balance equations, and then we can find the shear force and the bending moment. Okay, next let us look at drawing shear force and bending moment diagrams. So in the previous examples, we tried to find the shear force and bending moment at a single point. But oftentimes we are interested in the variation of shear force and bending moment diagram throughout the length of a beam. So in that case, we would want to draw the variation, and these variations are called the shear force or the bending moment diagrams. Okay, so there are some general pointers which you may recall related to links between shear force and bending moment diagram, right? So bending moment is the slope of the shear force. Shear force is the slope of the bending moment. Now a few other things are that wherever there is a concentrated load, there will be a jump in the shear force diagram. Wherever there is a concentrated moment, there will be a jump in the bending moment diagram. Okay, and also there is a convention that positive moment is shown on the tension side of a beam or column, but we may skip this for now. We will use the coordinate directions as we have been using. So let's say this is a given beam where we have to draw the shear force and bending moment diagrams, right? So again, the first step will be to draw the free body diagram and find the support reactions. Okay, and after finding the support reactions, one way of finding the shear force, bending moment, etc., is that we consider individual spans, let's say AC, CD, and DB, right? So in this case, since there are two concentrated loads being applied, we would realize that there will be jumps at these points. So the functional forms of the shear force and bending moments will be different. Uh, uh, Now the functional forms will be different. Okay, so one option is that we consider AC, CD, and DB individually. Okay, and so this AC is when x varies from 0 to L by 3. Okay, so we start from A, we have a cut somewhere between A and C, and again this is a right cut, so we show this positive sign convention. So from here we find S equal to P and M equal to Px. Okay, so for the span AC, we know that the shear force is P plus P, and the bending moment is Px. Okay, and next we move on to let's say CD, which is between L by 3 and 2L by 3. So again from here we can find out that S is equal to 0 and M is equal to PL by 3 constant. So again see that in AC the shear force was constant and with 0 slope. Okay, so the bending moment has a constant slope, or it is a linear function. In CD the shear force is constant but 0, so the bending moment has 0 slope and hence it is constant. Okay, so for the span CD the shear force is 0 and bending moment is constant at PL by 3. Okay, and you may also notice that if you put x equal to L by 3 in this P times x, which means this point will have the same bending moment from the left span and the right span. Okay, and similarly we can consider the span DB, which is 2L by 3 to L. So here we get S equal to minus P, okay, and M is equal to P times L minus X. So the shear force is minus P and this bending moment is P times L minus X. So basically the value of the shear force is negative and hence the slope of the moment diagram is negative. Okay, so so this is one way of drawing the bending moment diagrams. We may also approach the SFD BMD problems of simpler problems directly, okay, by considering the properties. So let's say this cantilevered beam is where we have to draw the bending moment diagram. First we find the support reactions using FBD, the free body diagram. Okay. For shear force diagram, we see that at A there is a positive shear force, right? And so basically there is a concentrated load applied. We have an upward jump here for the shear force of plus P. Okay. Now from A to C there is no applied load. So basically load intensity is 0. And since load intensity is 0, the slope of the shear force diagram will be 0, right? So it will continue at its value of P. So slope here will be 0, okay, and this is a positive shear. At point C there is a downward concentrated load, so there will be a jump equal to minus P here. So basically it comes back to origin, to the horizontal axis. Okay, and then from C to B again there is no load intensity, and hence the slope of the shear diagram will be 0. And since the value at C is 0, it will continue at 0 value. Okay, so this becomes the shear force diagram for this particular beam. Now for the bending moment, again we can have similar considerations, that at point A the bending moment value we know is minus PL by 2. From A to C the shear force diagram is constant and it has a non-zero constant value of P, which means that the slope of the shear force diagram will be equal to P. Okay, so since this is constant, this will be a straight line with a positive slope. Okay, and the slope also is known, so the slope is P. Okay, and you can easily calculate that if you go a distance of L by 2 with a slope of P, the vertical distance you will cover will be PL by 2. Okay, so since we started from minus PL by 2, we come to 0 for bending moment, and after that the shear force diagram again has 0 value. So the slope of the bending moment diagram will be 0, and since here at point C the value is 0, the rest of the bending moment variation is going to be like this. Okay, so in this manner we can draw the bending moment directly also. Let's look at one more example of a frame. So this is the frame shown for which we have to draw the bending moment and the shear force diagrams. So first we can find the support reactions from FBD. Then for such problems it is sometimes helpful to have an exploded version of the free body diagram. Okay, so basically if we cut at B, for the member BC, since we are cutting on the left, this is the positive sign convention, and again for member AB we are considering this upward direction to be the member x-axis. So again we are cutting on the right now, so for BC we are cutting on the left, for AB we are cutting on the right. And then using equilibrium for individual members AB and BC, we can find out the shear and moment and shear and moment. Okay, now we may consider individual members first. So if we consider the member BC, okay, so for member BC the shear force value at the left end is minus 35, right? So we go down to minus 35. Okay, and we also know that at the end C it has to come up by plus 65. So we know these two, and we also know that in the span BC the slope will be of the shear force diagram will be equal to the load intensity, which is 10, well rather minus 10, because this is a downward force. So we join these two lines, we join these 2 points through this line, right? So this is the linear variation of a shear force with a slope of -10, and overall this is a negative shear force. Okay, and using this shear force diagram we can draw the bending moment diagram. So we know that at the left end the bending moment is +150. Okay, so yeah, so it's here. So at the left end the bending moment is +150, and since the shear force is varying linearly, the bending moment will vary quadratically, and also since the shear force is all negative, the slope of the parabola will remain negative. Okay, so it will be a parabola of this shape. Similarly, we can draw the BMD SFD for member AB. So this, you can reason yourself that the shear force diagram comes like this, and the bending moment diagram comes like this. Okay, and once we have drawn these two individual shear force and bending moment diagrams, we can combine them and we can show it for the overall system. Okay. And of course, with practice, you may be able to draw the overall diagrams directly also, but initially you may want to think in terms of member wise. Okay. Let's look at one more example of a simply supported beam with an overhang. So again, the load intensity being applied is 10 kilonewton per meter. So first thing will be again to do the free body diagram, and once we are done with the free body diagram, we can look at the individual spans AB and BC. Okay, and in looking at AB and BC, then we can draw the shear force diagram and bending moment diagram. So notice here that since the load intensity is -10 throughout, the slope of the bending moment diagram will be -10 in both the spans. Okay, and due to this support reaction there is a jump here. Okay, due to this support reaction there is a jump here. Okay, and next we can draw the bending moment diagram. So a few things to notice here is that since at this point at x equal to x1 the shear force is 0, the bending moment will have a 0 slope, and since it has a 0 slope, that will have the maximum positive value for this span, right? And we will also be interested in this point here where the bending moment crosses the axis, or it changes its sign. So basically at x2 which is the point of contraflexure, right? And then so these calculations you can see that these are very simple, that the point of zero shear can be calculated from similar triangles, and similarly we can calculate what is the maximum bending moment from the area under SFD, and then we can calculate the point of zero moment, which is the contraflexure point, from the shear force area. Okay, so the relations between shear and bending moment diagrams become very important, and they are very handy in quickly trying to make the shear force and bending moment diagrams for different type of problems.